Thank you everyone for joining our learning session today. My name is Cameron, and myself, along with Frank and Alex, are going to be doing some discussing and sort of presenting on the support palette within Frame. The support pallet's main purpose. So the support palette provides a number of macros, structs, enums, and other things that are used in almost every Frame palette or frame-based palette. That could be like just types like const, unsigned integers of different, bits or bytes. It could be, different traits, all kinds of different things that you could use for this, or that are provided by this palette rather. It also provides over 91 traits with many different utilities, from checking the storage version of a palette to ensuring that an extrinsic is of a certain origin level to make a call. Most obvious or most simple one would be like something that requires root access or some sort of special origin. And it also provides modules that generally make the development experience easier for Frame developers. And those are modules that expose different macros that, like we mentioned before, sort of take some of that manual code that you'd have to write without using Frame and sort of generates it for you. So we'll see examples of that later on in the presentation as well. And as a core palette, all other Frame palettes, as mentioned before, do depend on the support palette, as well as like other palettes within the core palettes like system, executive, benchmarking, etc. High-level features. So the support palette does many different things. So it gives certain traits like that allow you to verify an extrinsic call, such as the extrinsic call trait, and also traits that allow you to inspect that call's metadata, such as get call metadata. It allows you the ability to get details about like the current validator set within Polkadot, for example, or Kusama, using the validator set trait and its associated methods. It also provides metadata about the runtime storage using the get storage trait. So if you want to check the version of the storage before you run some other logic within your code, you can do so. It also allows you to define operations that you want to occur on genesis of your runtime. So if there's some sort of special logic that you want to happen on genesis, you can actually define that using some of the traits within this palette. So these are common things that a developer might actually, want to do, inspecting an extrinsic or getting some metadata about some value that you received or some value that was called, or just inspecting the chain itself in the runtime. And it also handles other low-level tasks like incremental changes to account IDs, determining whether a type contains a particular value, defining what can execute a block and the block's extrinsics. So these are just some of the traits. As I mentioned before, there are over 90 traits within this palette, and the things that they sort of cover range greatly. So other high-level features. So generally, the modules, as we've covered before. So here are two examples of modules. The tokens module, and this is provided by the support palette and defines utilities for working with fungible and non-fungible assets. So things like checking balances or transferring and things of that nature. And also the palette macros module. This defines macro stubs for all palette macros, such as palette weight, or which allows you to define the weight for a call, or palette genesis build, which allows you to define the genesis configuration for your runtime. So these are all like very core and very powerful things that this palette exposes for developers to be able to use. Along those lines, the palette macros. So the support palette really is very integral to defining palettes within Frame generally. And some of these macros, these attribute macros, such as palette call, are found all throughout the code base of every Frame palette. So palette call is used to define callable extrinsic functions within the palette, or palette event. Here is another macro which is used to denote like different events that can be emitted from your palette when certain things are happening or certain actions are occurring. Or for defining your storage types, you can use palette storage, to define, multiple storage types depending on your needs. the needs of your specific chain or runtime. And also any errors that you want to define can be defined using pallet error attribute macro. So like if a transaction fails, maybe you have a custom error that you want your runtime to emit to for people to see, exactly what happened. And then touching on traits again, there's a myriad of traits here. These are just 2 examples. So hashable just gives you the ability to define a type that is hashable within Substrate. And it has like required methods that may need to be implemented, such as Blake 256 or other hashing types. And on runtime upgrade, which is something that's very, very powerful, giving you the ability to express something that should happen when your runtime upgrades. And obviously, that's one of the key aspects of building a substrate-based chain is having forkless upgrades and being able to upgrade your code or your sort of librs easily. And so if you want to have some sort of custom logic whenever you did so, you could easily have that by implementing this trait here. As previously talked about, so frame support is one of the core pallets, which means it's used by all other pallets within frame. I think there may be one other pallet that's more low level, but it exists outside of frame. I think that's pallet meta, I believe, but this along with some of the other core pallets are, pretty much used by all other pallets, and they depend on the functionality and utilities that are exposed and sort of pre-built within this pallet. And just to take a look at so just to show like all the different traits that this pallet has, like these are just some of them. So things from like queuing messaging, executing blocks, extrinsic call that I mentioned before, get storage version, tons of different things that you can sort of use this palette to do. And this is why it's highly used within frame itself. How it's used in Substrate. So here are 2 little code snippets of this palette being used, the support palette being used. So here's the first one comes from the pseudo palette, and it's just a simple definition of an error here. So the only error here is require pseudo. So I guess if a call is made that requires pseudo and it doesn't actually, the origin is not of pseudo origin, then it will emit this error here. And this is a pattern that you'll see all throughout substrate-based or frame-based palettes, rather. And the second one here is an example that comes from the executive palette. Here, custom on runtime upgrade struct is defined or declared, and then the implementation of on runtime upgrade for that struct is here. So on runtime upgrade, it's going to return a weight here, which is tail expression, and it does some setting and storage, and it also deposits into blocks event record. So it has this event here, and it deposits it into the blocks event record. So for your case, you could define an on runtime upgrade custom implementation for your chain, and if you wanted to do something different or something very special based on the logic of your chain, you could do so. And this is how you would sort of do it. And this is another very common thing that is used that originates from the support palette, which is construct runtime. So basically setting some constraints and then providing all the pallets that you want to actually be a part of your runtime. So here, actually, this example, I actually cut off some of the pallets, but pretty much customize your palette exactly how you want, or your runtime exactly how you want, with whichever pallets that you want to be included, giving you that sort of modularity and composability that is what Substrate and sort of frame is all about in the first place. So, and since every runtime needs to be constructed, for every runtime is going to be relying on the support palette to do so. So once again, very, very integral to frame developers, day to day. And here, just want to do a little bit more talking about macros. So macros are basically code that writes other code, allows you to extract repetitive operations, as sort of we talked about before, and simplify the code that you need to write. So instead of, when you define a storage type, instead of having to worry about how do I put to that storage or get, read from that storage or mutate it, those things are all, sort of handled by frame macros for you. And you can just focus on the specific logic that you want to actually handle. So there's typically two different kinds of or flavors of macros. So there's declarative. That's where declare a pattern and compare a result of an expression to that pattern. Executing additional code if patterns are matched. So here an example is ensure, the ensure macro. So you could say ensure that some value meets a threshold, or ensure that a value matches a certain expected value, and then any code that you wanted to execute beyond that could be executed. But if not, then maybe an error is emitted. And then there's procedural macros, which are more similar to functions. They take code as input and they produce code as output. Example here is frame support procedural. And those are like custom derived attributes where if you have a custom type that needs to implement or satisfy certain traits, you can just derive those traits, the already existing implementations of those traits without having to create the implementations yourself if you have no need to do so. So that's a common thing that's done within Rust code in general, but also within Frame and Substrate. And that's useful for custom runtime types that, again, must satisfy specific traits. Attribute-like, so you can create new attributes to generate code. And function-like, define macros that operate like function calls to generate code. So that's also a part of the Frame Pallet outer macro pattern. So you'll have these inner macros, and then you have an outer macro like frame support palette, which then consumes those macros and generates and expands on the code that you gave it to create those pre-built sort of APIs and functions that you don't have to create yourself, and thus allows you to have a better development experience within Frame or as a Frame developer. And you'll see some of that later on in the presentation as well, where you'll be able to see some non-expanded or code that uses macros, and then the expanded version of that code as well. And it really makes developing within Frame, much better, and makes it easier and sort of gives you more powerful ability to express the things that you want to without getting bogged down with details of things that every palette or runtime or blockchain will need anyway. So yeah, that is the end of my section. I don't know if Frank, you want to take it from here.
So I'm just going to kind of focus primarily on the storage sort of module within the overall sort of Frame support palette. The goal being just to sort of break down the various components which enable runtime storage definition within a particular palette. So just starting off, so we're just going to kind of look at the typical sort of setup, and all I've done is just taken a few examples from last week's presentation that the palette used there, the Frame system palette, just to kind of explore how typically you would kind of set it all up, and then more importantly, what sort of components happen underneath to kind of realize all these sort of deep little tricks that go on. So kind of starting from the top, we've got the sort of palette attribute. And really that's kind of just in the background when you compile it, it sort of implements this additional trait called the storage info trait on this sort of palette type. And all that storage info trait is going to do is it's going to return sort of metadata in terms of the actual size of all the types. And that information is actually then used in the state transition proofs in calculating the size of it. So you can use like the unbounded one at the bottom, which we'll touch on later, to sort of annotate certain storage items which you maybe want to exclude from that. The next one down is the generate store attribute. And all this one really does is it defines a trait called store. And then in terms of the generation process, all it's going to do is that for each storage item, it's going to create an associated type on that trait. So in this example, it would be block weight and extrinsic data. And really what that allows you to do is to refer to those storage items through the traits, store trait on the palette. So an example here is, palette as store block weight. Then the next item is a storage version, which you don't typically often see for newer palettes, maybe as palettes have progressed over time. The idea being here is you can kind of define the current version of the storage, and the main goal around that is just aiding with storage migrations. If we then drop down a little bit further and start looking at the storage items themselves, so we've got this palette storage attribute, and the power behind that is really it generates this storage instance trait implementation for the storage type. An example of the trait on the right is kind of just shows you that all it's really saying is, was the palette prefix. So in this instance, it'll be the the name of the pallet that you've given it in the construct runtime that Cameron showed, and then more importantly, the storage prefix, which is typically by default is just the actual name of the type that you've given it. Then the next item down is the whitelist storage, which is kind of very rarely used, but that allows you to sort of declare a particular storage item as being sort of exempt from benchmarking. So when you're running your benchmarking and calculating the size or the weights for a particular extrinsic, if there's something that's sort of very crucial or very sort of low-level system-based, which we'll see a little bit later in the transaction example, then you can kind of exclude that. The next one down is just the getter, and kind of all that's really doing is just generating a nice little function for you attached to the pallet, so that you don't have to use any of the other sort of weird syntax to be able to get at the storage. You can just use a function to get at it. Then the most important line really is just the actual definition of the storage item. So all this is type alias. So we've got the type definition, the name, which is generic over some type T, which is the config item that's used, and then that type alias refers to the actual storage type that you want to use. In this example, it's storage value. The first type parameter is the prefix, which normally is just an underscore, and the way that works is that that'll essentially refer back to the storage instance here to be able to generate out the prefix for the particular pallet, and all the storage items within that, all the data items within that storage item. And then in this example, because it's a storage value, we've just got the consumed weight, and then the type of query, that when we query the item, the storage item, what sort of type of value are we expecting to come back. Then just sort of briefly to mention the two additional ones. So on this one, we've got the storage prefix attribute. In this example, I've just called it learning session. And really what that does is just allows you to define your own storage prefix rather than relying on this storage instance trait mechanism. And then it also then allows you to essentially name your generic types, even though those generic type names are just kind of completely ignored when the macro runs. More for developer experience. And then finally, as I kind of hinted at earlier, the unbounded attribute, which essentially, as I said, if a particular storage item is going to be containing, say, a vector which can grow to any size, normally you'd have to either use a bounded vec, but in this instance, we could just declare it as unbounded, and that's going to then exclude it from the straight state transition proof size calculation. So that is just a sort of overview of how we typically use it. If we now just look at an overview of the various submodules within the storage module. So at the root of the sort of module, you've got your typical runtime API traits. So storage value, storage map, etc. And that's kind of the API that you're used to using when you actually interact with the storage item type in your runtime. But then the next level down, we've got something called the generated traits. And these really are just an internal set of traits on which the storage traits above are kind of implemented. We'll go into a little bit of detail in a minute, but really it's you can kind of think of the generated traits as kind of like location or addressing, like how do we find our storage item in the underlying key value store before we actually then do certain actions on it. Then the next submodule is the types. So as mentioned before, these are the actual storage value type structs. That when we type alias, when we're declaring our storage items, it actually references these types. And then within this module as well, we've got the query kind trait, which has got three different options, being the option query, result, and value queries. And as I sort of mentioned, that's just determining how, when we query for data, how we want to handle whether it exists or not. And then there is also one other additional one, which is the storage entry metadata builder trait. And you can kind of think of that as just a trait that one of these storage item structs will implement to provide some metadata, which then feeds into the overall metadata of the Pallet runtime, which you can imagine kind of feeds into Polkadot.js apps or Polkadot.js API. And then finally, the last two little submodules is the transactional, which I'll touch on briefly. And that just kind of provides a little bit of functionality. It's a thin layer of functionality around transaction storage. And then I'll just finish up in terms of just pointing out a few interesting things on migration. So to try and sort of explain how these sort of components fit together, it kind of seemed easiest to maybe draw a quick diagram. So at the top left, you've got the storage value. I'm just going to call, for the sake of ease, the runtime storage API trait. So you can imagine that when you're interacting with a storage item in your runtime, this is the API that you're going to get used to or would usually use. But then kind of using that layer or a sub layer or an adjacent layer to that storage value is the actual generator. And as I mentioned before, you can think of the generator perhaps as like a mechanism for addressing some storage item within the sort of the overall sort of state of the blockchain. So you can see here we've got the module prefix, storage prefix, and then storage value, final key. So it's just really saying, well, how can we find this particular value within the storage, and then the actual items in the runtime trade will allow us to then manipulate that data. And then within that sort of module, there is a generic implementation of these traits, which I'll touch on briefly. And then sort of most importantly, we've got that storage value struct, which is the type alias that I mentioned initially. And that storage value implements the generator trait, as well as the storage info trait, which is that POV state transition proof that I mentioned, as well as the metadata builder, which I mentioned as well. So top bit is for the POV size calculation. The bottom bit is for the metadata, which appears in the runtime. So if we just kind of briefly just look at some of those in a bit more detail. So this is that runtime API that I mentioned. You can kind of see that same interface. But most importantly, if you look at the comments, it kind of says details and implementation can be found at generator storage value, which we're going to look at next. So looking at that trait, you can kind of see, again, it's that same sort of addressing type goal of the trait, but then also kind of provides a few additional things, which is like conversions between optional values, because some storage item may or may not exist. So it's just how we go about handling that process. And then most importantly, in the case of the storage value, we're just looking for the final key, which you can see in terms of the definition. It's actually just creating the storage prefix using the module prefix, which is the method above, and the storage prefix, which is the actual storage item name. So moving along then to the kind of where most of the bulk of the implementation exists for this particular example of the storage value type. So you can see here that really all this is doing is it's implementing this trait, which is the runtime trait of frame support storage value of some type T, and it's implementing it based on some generator type, which implements the frame support storage generator storage value type. So really what happens is we're providing a generic implementation for any type that implements the storage value. And you can kind of see here that it's referring back to that same storage value final key that we mentioned before. But more importantly, if you look at some of the actual implementations, you can see that when we're checking to see if the value exists, it's actually calling into the unhashed module to see if it exists, passing in that same key that's defined. And then likewise, the get is calling into the unhashed module with the get. And it kind of follows that same pattern throughout with the try get and the put. So that you kind of think as this implementation is doing the heavy lifting or the definition of, once we know where content is, how do we get it out and manipulate it to make some change to the state. And then just briefly to touch on the unhashed implementation. So you can see really all it's doing is just deferring to the storage primitive crate for the actual implementation. The get is slightly more interesting, and that is obviously returning the item from storage. And then if it exists, it's trying to then decode it to the required type. If it is successful, then it maps it to some value. Otherwise, it logs an error and then returns none. And then likewise, the put is just a reverse of that. So it's going to take in some typed value, encode it, and then pass that onto the storage primitive to actually set it into the storage using the key and the slice in this example. So that's kind of how sort of all the bits kind of fit together thus far. But then if we look at kind of the most important part, which is that same storage value type struct that I mentioned earlier, you can see there isn't a lot going on at all. This is kind of the gist of it in essence. So all it is really is just that type definition, and then we implement the generator storage value, which if you recall was just the addressing. And in this instance, all we're doing is we kind of deferring to say, well, when we trying to address our content, we want to base it on the prefix, which is the generic type that's passed in. So you get the pallet prefix and the storage prefix. And then again, we've got those converter functions that I mentioned, which are then sort of also deferring to use the query kind to actually do the conversion. And that's something that we'll look at next. So the query kind trait is fairly straightforward. You can kind of see that it's either an optional value or a default value in terms of the modifier for the metadata. But more importantly, you've got those same two methods again for converting the values. And I'll just sort of contrast them in terms of the three different implementations to see how similar they are and how sort of simply they have been implemented and how powerful it is as a result. So the option query, really, because when you're querying it by default, it's going to be an option on whether it exists or not. All we're doing is we're just returning the actual value for both of the implementations. So not a huge amount to actually look at there. But if we then contrast that to the result query, you can see now that the query type is different. It's a result of some value or an error. And in this instance, we're taking in an option. And then if we have an option, which is some value, all we do is we just wrap it in an OK. Otherwise, if it doesn't exist, we then call the get function on empty type, which in this case is going to return the error that we specify when we actually call the particular method to return an error if something doesn't exist. And then the other one is fairly straightforward as well, so I won't go into that. And then finally, just to contrast it to the value query, which again is just taking in an option. And then if the option doesn't exist, all we're going to do is call the get method on empty type. And that really just allows us to say if something doesn't exist in storage, then we want the default value to be X and then return that. And then the other side of it is just wrapping it in sum. So that is it in terms of the query types. So then just briefly to look at the transactional side of it. This is a very, very thin layer, but I did kind of find it a little bit interesting. It obviously relies heavily again on the storage primitives. So in this instance, you can see it's importing the commit transaction, rollback, and start transaction. But more importantly, it allows the definition of the maximum number of transactions that can be sort of nested or stacked, as well as it defines where in storage we're going to store the current layer, and then also the type of the layer. And if you look at these two definitions below, you can kind of see that as we create a new storage layer or a new transaction layer, all it's going to do is it's going to update the storage using the unhashed module again, and then put some value into storage. So incrementing will just get the current value, increment it by 1, and put into storage. So you can kind of imagine that as layers get stacked upon, it's going to be reading and writing storage to kind of keep track of where we are in the stack of transactions. If we then look at the implementation of that with transaction, and this is something you would sort of typically use to wrap a bit of code in a transaction. So you can kind of see that it takes some function, and that function is going to be executed, and then depending on the outcome, we then choose whether to commit it or roll it back. And then depending on what the result is, we then obviously just call back into that storage primitive to actually perform the necessary work and then return the results. So the important thing to note here is that obviously we're dealing with transaction outcomes, but then there is a small layer above this, which just kind of improves the API somewhat, which in this instance, it just uses the standard Rust type of a result. The idea being is that, when you start using this from your runtime API, from your runtime, you just have to worry about interacting with whether something is an OK or an error, not having to worry about the transaction outcomes. So you can kind of see that the function on the closure that gets passed in is called here in the body. And then if it's successful, it's handling the whole process of returning the commit type, which we saw earlier. And then the main reason that I kind of brought this whole thing up is that if we look at a bit of code from last week that was demoed, which was the whole set code extrinsic, which upgraded the runtime, you can see above that that's the code that you would see when looking at the Pallet code. But then through the process of compiling and expanding the code, you can actually see that an additional little wrapper has been added here, which essentially adds an implicit storage transaction layer. So you can see there's that with storage layer that I mentioned, and that's the code that we've taken from above. So really sort of demonstrating how the frame macros are wrapping something in the transaction implicitly for us without us or a developer having to worry about that. And then just to sort of finish off very briefly, and something that was sort of touched on at the beginning, just the migration submodule. So really it just has like a number of utility functions that allow you to do sort of actions on arbitrary data types or collections of items. So you can kind of see move prefix, move storage from pallet, move pallets. The idea being that, as your storage needs evolve over time, you can migrate the way the data is stored, one particular storage version to a new one. And as sort of Cameron mentioned, we've got the on runtime upgrade hook or trait. And really just kind of on the right, we've just got a small little implementation of that, which kind of demonstrates it. So we can kind of read out what the current version is, what the unchained version is. And then based on those, we can have a series of match statements, which allow us to sort of migrate the storage to take it from one sort of structure and store it in a different sort of structure. And obviously that gets executed as part of the runtime upgrade.
Okay, so now we're gonna do a deep dive into the macros that the Pallet support provide us. Cameron has explained in the introduction what macros are, but just as a brief description, macros is a tool for making the compiler to write code for you. So it's very helpful for us because it's gonna be writing code for us that we don't have to write some of the code. So the idea of this is to see what macros the Pallet provide, and we're gonna see then how powerful that is for a Substrate developer. This is from the documentation of the Pallet itself. These are all the macros that the frame support provides us. So if at some stage you need to check one, I do recommend you to come to this website because it's very, very well explained. I decided to pick some of the macros that I'm pretty sure you already seen. If you have developed a pallet or have checked some pallet, or even if you have only checked the Substrate documentations, I'm sure that you're familiar with these pallets, but you didn't know what they were for. And now, after this deep dive, I hope that you realize how helpful they were. So the first one is pallet, the macro pallet. That's required to declare a pallet. So this pallet attribute macro defines a pallet that then can be used with custom runtime to build the runtime. That's the syntaxes. This is the hashtag and then the brackets and the pallet inside. So when you define a pallet like we see in this code, pub mod pallet, we put the macro in the top. And then what is gonna do that is to check that all our construct that all the things that the pallet needs are there, and it's gonna extend our code to have more extra code to help up to with the functionality of the pallet. Inside of this macro pallet, inside of this module, there are some attributes that are depends of the macro pallet that you're familiar to. It has similar syntaxes. It has the hashtag, the brackets, and then have pallet config or pallet events or pallet errors to define some of the components of the pallet. Some are mandatory and some are optional, but helps to work with the functionality. And then it's worth to mention here that there's also an argument that's for a few months ago that was introduced, that is called def mode, that you can put that inside of the pallet macro, and that helps you to just focus on the business logic. So the compiler is going to be less restrictive, as it's not going to do all the checks that usually will do for a pallet that is going to go for production, and just for you to tinker around and to play with the business logic. This code that we have here, that's a skeleton of a pallet. There is no implementation here, but we can see the skeleton of a normal pallet has. All the pallets for frame or the pallets that you're going to build will have probably that. In the top of the file, in the top of the code, we have the macro frame support pallet, and then we have the different attributes that I mentioned before. So the first one is pallet, that this allows you to specify the pallet information. This is something that, for example, is mandatory. So you define this pub struct pallet. And then there is also another that is generate store that creates the trait store and implement it inside the pallet. The configs to define the configurable option. Then we have the pallet event and pallet errors that allows us as a Substrate developers to very easily define the events and errors. Then we have storage for the storage and call that this is for the Pallet dispatchables for the extrinsic code of the Pallet. Here in the right, I put some that probably you are familiar to. Pallet constant, that's the one that this macro is for the constant that we define inside of the config. The pallet weight for the weight of the extrinsics, and this pallet getter. That what it does is generate a function myGetter fn name for us that is retrieving information from the storage. And then other optional like hooks, Genesis config, and origin to do more things in our pallet. Let's see a bit the code to see more example and to try to understand the power of the macros. So this is the Substrate node template, and inside of the Substrate node template, we have a pallet template that is basically a simple pallet that we can see has the same skeleton as before. So first we have here the macro pallet, then we have the different attributes, pallet, config, storage, pallet event, pallet error. For this template pallet, I just add a couple of things. I add here this macro pallet constant, the attributes, to define a constant that in the config for the runtime. But it doesn't do anything. It's just you're gonna see later why I put that to show the functionality of the macros. And then I add also a line here in one of the function, in one of the extrinsic do something. I add this line, ensure this is a macro, ensure. That basically what it does is check that one of the parameters that goes to the extrinsic, the something, is greater than 0. So we have a full pallet here in just 110 lines of code. We have our pallet with the functionality, very basic functionality, but a pallet that has the errors, has some events, it has some storage, and it has a couple of functions that does something with the storage. What I want to show you now is how it looks like after the compilation and how it was the real code of this pallet, the code that the macros generate for us. So there is one tool that is called Cargo Expand that you can install doing cargo install cargo expand. So when we run this tool for this file that we are checking now, for the template of the pallet, what it does is print you all the code with all the macros, so the full code that basically is what the compiler is gonna generate. I take it here instead of looking that into the terminal, so we can more or less compare. So it's so here we can see that this is the poof mode pallet. And then it goes through the same imports. And then here we see the poop struct pallet. So it has taken off the macro pallet and it has generated some code for us. So here is the trade config. So all this code has been generated because of this macro pallet. So in that scenario, it has had some functions like a clone function for equal for the debug, that helps for a struct. So we don't have to code these things because they are embedded with the macro. If we go down, so we can see the same for event. So it has a lot of information and it has the same. So if we see the extended file, so the file of our pallet, the real code of our pallet, it has more than 1,400 lines of code. The pallet that we have to care as a Substrate developers, it only have 100. So you can see here all the code that the compiler has had for us, thanks to the macros. So let's take a look for this example that I've added. So the macro ensure, what it does. The macro ensure here is only checks that the value something is greater than 0, and if not, it throws an error. So basically, what it does is transform that into code. So if the normal code of that, if it's not something greater, is not greater than 0, it's called the error. It returns the error that we have put there. Let's check the code of this. So we go into that. That's the code base of the support pallet, where all these macros has been implemented. So here we try to find the ensure macro. So this is as Cameron explained when he explained the macros, he said that there are two types, declarative and procedures. That's a declarative macro. To generate that, you have to start with macro rules and the exclamation symbol, which is a macro itself, and then the name of your macro. And then here you have your code. The code of this macro, basically what it does is generate the code that we have seen before. So it's a series of regular expressions that transform some of the code, some of the parameters. So the parameters in that case evaluate the expression x and return the expression y. So this code, it turns into that code with the parameters that we have put here. There's something greater than 0 and the error. So that's why this macros is called like metaprogramming, because it's Rust code that is generating Rust code. We will take a quick look now into the implementation of the macro palette. This is more complex than the one that we have seen. This is the other type of macros. This is the procedural macros. You can have more logic here because you can have a real Rust function that it does more things. So, but the idea is the same. So it has an input. It takes an input of a code and it returns you an output that is another code. In that case, the code is this type, the token stream. So it has a token stream that's going and it go out another token stream that is the extended code that we have seen before. So here it has the attribute and item. So if we come back to our template, and for example, we see this config and config, this config attributes. So this is so what is gonna do the macro palette is gonna go through all the code inside of the poop mod palette, and it's gonna stop in each of the attributes. So it takes the attribute config, and that's the item, the other parameter of that function. So all the code inside this attribute, the poop trade config and all this code, is the item here. And so the process here, what this macro function does is first it parses all the code, and second it expands the code. So it parses all the code, it analyzes it, and then it parses. If we see that's in the folder procedural in source, there is one that is called Pallet. That's where all the implementation of the macro palette is. So we see that it has two folders, parse and expand. So we take a quick look now in parse. What parse does is basically what I say, no? So it has all the different attributes that can be defined inside of the macro, palette, and know how to parse them. So in that example, if it's the attribute config, we know that we have to go to config because we know here how to parse all the information inside. And secondly, what it's gonna do is expand all this code. So now that we have parsed all the code that goes inside, we'll go and we say a config. So now we know how to expand. We know what code we'll have to add to that. So we go to there and we expand the code of the config. So yeah, that's the idea of the palette macro. I wanna see another macros that I'm sure you have seen before. From these two first, construct runtime and parameter types. If you have worked with the runtime of a node, there is in the runtime of Polkadot, the runtime of Kusama, or the runtime of your node template, you have seen these two. The first one, construct runtime, that's used to construct the runtime from the list of pallets that you have implemented. So basically it goes through all the list of the pallets and generates all of the data structures that have been declared and implemented for that pallets to include them in the runtime. And the parameter types is used to create a new implementation of the get right. So let's take a look into the code to understand it better. So that's again, that's the Substrate node template, but instead of go to the palette now, we go to the runtime file. So the librs that we have here. So we see that here is all the information, all the runtime that our node has. Again, we can see the number of lines. To see them is 600, and we go to we go to the one that are familiar for us when we implement our pallet. So we implement here the pallet template. And we can see now here we can see the two macros that we've been talking about, the parameter types and the construct runtime. The parameter type, now you know why we add this useless parameter in the config, it's gonna be just to show what parameter types is doing. So now we do the same as before. We do the cargo extend into that file to see what it looks like in config when it is being compiled. So we see now that the 600 lines of code of lib now is the extending all the code from the macros is more like 6,000 lines of code. So we can see how helpful are these macros here. We take a look we try to find in that file the parameter test to see more specific examples. So we see that here we define this parameter test to be a U32 that is equal to 5. And this parameter type, what it's doing is basically is injecting this code for us. So it's coding, is adding this code for us. That basically is the implementation of the trait get for this parameter. If we take a quick look into the code of this one parameter type, this is also a declarative macro. So remember all the declarative macros are implemented with the macro rules and the exclamation mark first, and then the name of your macro. And we can see this is a bit more complex than the other that we've seen from the ensure that we have seen before. But the idea is the same. It's a series of regular expression that takes some input and add something or do some code substitution or things like that. And then we have the construct runtime that, as we say, is gonna take all the different pallets that we have for our runtime system, timestamp, aura, and the one that we add, the template palette that we add, and we're gonna go through and it's gonna add all the different data structure and all the things that we need for these pallets. So that's all the code that is gonna generate. If we're gonna take a quick look as well now here on how it's implemented the construct runtime. That's not a declarative macro. That's a procedural macro, same as the palette that we have seen. This is in the folder procedural and then in the lib file. So the idea is the same as the palette. It has an input that is a token stream. That means a chunk of code, and it's going to return another chunk of code with the code extend, so with more code than before. So it works similar. So it goes here, it's the construct, and it's going to do the same. So it's going to do the parsing and then the extending of the code. And finally, we have also a couple more that I think is worth to mention because we have used, probably you have seen there, is assert OK. That is a macro that panic if an expression doesn't evaluate OK, and assert noob that evaluate an expression, assert it returns an expected error value, and that runtime storage has not been mutated. You can guess that this is going to be for testing purposes. So we go to the node template. If we come back to our palette template that we have been developing, now we have the part of the unit test. This is the code of the unit test. I do the same again, the cargo expand to see all the code that is gonna expand from this file. And here you can even see more clearly how helpful the macros are, because this test is like, even if you are not very familiar with Rust, it looks like it looks easy, not very complicated to create a test. So for example, if we look here, here we are just checking that the function that the extrinsic that we have code for the palette, we can check that it works fine, and we can check if that is actually writing inside. So we can check that the storage has changed in just 2 lines of code. But if we want to see what macros does, so this is the text expanded file. So this 27 lines of code, this turns to be more than 3,000 lines of code. 3,000 and 400 lines of code. So yeah, it's even an example more clear about how useful are. Here is that big because it includes the things for the mock to mock the test, and also this tag this test is also a macro itself to build all the test environment. But if we want to check the example that we mentioned about the assert OK, let's try to find here this name of a function instead of this big file. Okay, yeah. So here is the function. So the assert OK that we mentioned before, that basically what it's doing is that our function works OK, and it returns a value that we want. No, that it works OK. Yeah. So we have this code. This assert OK is gonna turn. I don't know if you can see now very well, but this assert OK is gonna return. It's gonna code for us all this code. So basically, it's gonna check if it's OK. If it's not, why it's panicking or how it's panicking. Let's take a look of this code just a bit. Again, this is a declarative macro rules and the exclamation mark, and we try to find the assert OK. So here we have the code. So again, this is as we see in the ensure, this is a bit similar to that. So it's taking an expression and with regular expression is and patterns to code substitution to grab more code. So Rust code that generates Rust code. And the same for the assert noob. So the assert noob, what it's doing is taking an expression to see that is expecting an error, so it's throwing an error, and also checking that the storage has not been mutated. So we see the example here of the other test that we have built here, and we can check that. So this is the code that the assert noob is generating. So first is checking that the value on the left is equal to the value on the right, and after is also checking that the storage of our node has not been mutated. So just this line of code is generating all these lines of code.